Hi everybody, this is a video for Math 240, 341, and I've already added some things, but this handout is given on Canvas. You can get it. And what it is a proof of the Pythagorean theorem using this diagram that's attributed to Bhaskara. Actually, I think Bhaskara the second. There's more than one Bhaskara. And he was a mathematician in South Asia hundreds of years ago. Now, he didn't lay out in words, step by step, the proof. He just showed the diagram and said, behold. So it's kind of interesting. So I kind of like, okay, let's take that diagram and unpack it and kind of think about more step by step what is being used, try to justify it. Before I move on, an important note is another reason I like using this is it shows the multicultural nature of mathematics. Mathematics has been done in all cultures, from ancient times to the present. We tend to, in the United States anyways, have a Eurocentric slant toward mathematics. We sort of think of it as starting with the Greeks and, the Europeans developed other stuff. And then, now everyone does it our way, kind of from the perspective of kind of the European. And that's not true. There's been wonderful, of course, mathematics done in that tradition, but that is not the whole and end all. And I think with a lot of students in K-12, it's important for them to realize the global nature, the multicultural nature of mathematics. So this is a nice example of that. Okay. So this is a statement reason. Some people call it a table form of proof. It's very stark, right? The idea is just as clearly as possible. This is what I'm doing, and this is why I can do it, right? And often, at least at the K-12 level, they only want to go one tiny step at a time. And the reason they do that is not so much to be a proof, but it helps, it's intended to help students learn more logical arguments, and an introduction to axiomatic systems, how we take some things for granted and then we justify other things using the things we've taken for granted, right? So the difference between an axiom, something you take as given, and the theorem, something that you derive from other things. Now, it's important to note that most mathematics is not done with these kind of proofs. Most mathematics is done with narrative proofs. Those of you who have had 211 sort of know this. That class tends to emphasize narrative proof. However, I like to do some of this type of proof because it happens a lot in high school textbooks. Okay, that's all the prelim. Now let's take a look at the actual diagram and proof. So generally you start with what's given. You should kind of always start with that. And so notice in this thing, we're given that we have a square, that A, B, C, D is a square, and we're given that the side length is A plus B, so that the whole thing is A plus B, the length of every side, A plus B, A plus B, A plus B, A plus B. Okay. And we're also given that these lengths, AE, BF, CG, and DH, are all length A. Now notice the second step seems really obvious, so you might not see it in all the proofs. The fact that if the whole thing is length A plus B, and so if let me run it through here. If AB has length A plus B, and AE has length A, well, guess what? EB has to have length just B, because A plus B minus A equals B. So a lot of times in our proofs, we'll just say it's properties of algebra. And sometimes you might even skip this step and see it as sort of common knowledge. Okay, what's next? So we're going to use the definition. We're given that it's a square. Well, since it's a square, not only are all the sides the same length, but also all the angles are 90 degrees. So the definition of a square is it's a rhombus, equilateral, quadrilateral, and it's a rectangle, all four squares, 90 degrees. Okay, and so we just justify that from a definition. And notice you don't prove a definition. You just sort of state it. You know, it's a definition, which is different than an axiom or a theorem. Okay, now we can talk about these triangles, and all of those triangles are congruent. So, for example, this triangle, all four of these triangles are congruent, and there we're using side angle side, right? This one's congruent to that one because short sides are the same, middle sides are the same, and guess what? The included angles are both 90 degrees. Okay, then we get that all of the hypotenuse have to be the same, and that's by corresponding parts of congruent triangles. So let's just call all four of those C. Okay, and we also know the other angles are also congruent. So BEF, BEF. So let's call, I didn't give them a name, but let's call this angle alpha. So all of these little angles here are alpha. Okay, and now, since this is 90 degrees, look at these triangles. I got a 90-degree angle and an alpha. We know the other angle is 90 minus alpha because the triangle sum theorem says that all three angles add up to 180 and just angle addition. And we call those type of angles complementary. So this angle here, all of these angles are 90 minus alpha. That one, this one, this guy here, and this guy here. Okay. Now we can show that this angle inside, the inside angles, are 90-degree angles. And that's because these three angles add up to a straight angle. And if these two add up to 90, then by subtraction, these guys have to be 90. So we know that these four angles are right angles. I skipped a step somewhere. I'm sorry, I skipped this step here. When we got them all congruent, we said all four of these guys are the same, which I call C. And notice that a quadrilateral with four equal sides is a rhombus. So that was a step here that I skipped. So now notice that this inner guy, EFGH, we've shown that it's equilateral, it's a rhombus, and all four angles are 90 degrees. Well, guess what? That's what a square is. So that's what we needed to show, that these four triangles are congruent and that this quadrilateral EFGH is a square. So those are kind of the important steps. So notice, that's kind of the meat of the proof. Oh, hey, those triangles are all congruent, and we need to show that that other thing is a square. But when you just see it without me talking about it, you wouldn't realize that steps 3 and step 10 are more important than other steps. Okay, well now just this guy is C squared because it's a square with side length C. ABCD, it has is A plus B squared because it's a square with side A plus B, And a plus b quantity squared equals a squared plus 2ab plus b squared. That's just algebra. And notice each of these triangles is 1/2 base times height. So by the triangle formula, each of these triangles is 1/2 AB. So all 4 triangles add up to 2AB. That's 14. So now we have that the whole thing, a squared plus 2ab plus b squared minus the 4 triangles equals the inside thing. And so a squared plus b squared has to equal c squared, and that's the Pythagorean theorem. So kind of the point of this video was just to talk through one of these statement theorem type proofs. We're not going to do too much of this, but it's important to do it some, because especially the future teachers, this will be something that you'll see in high school geometry texts. And also, geometry is a nice subject from which you can teach and learn logical structure, which is, nice for areas outside of math. I mean, logical structure is nice if you're going to be a computer scientist, if you're going to be a lawyer, right? If you're going to be a businessman, being able to kind of follow a sound logical argument is quite important. Okay, thank you.